This is Team 10, and our final project is on finding the location of acute infarcts using CNN.
This is Sai Shri. The given input was 50 classes, which we have processed and combined it into 46 classes. But the neural network need more amount of data, so we have used data augmentation. The techniques used in this process are like rotation, width shift, and height shift. And we didn't use horizontal flip and vertical flip. And the data we have loaded.
Yeah, so it's Apeksha here, and I will be talking about loading the data. So before we had not grouped the data, so that time we had got very less accuracy. So now we have grouped the classes. So this is the dictionary that is mapping label of the map label to the group classes, and next dictionary, which is called combined, is mapping group classes to the label of the group classes. And then we are loading the data. So yeah, before loading the data, we had done a couple of things, as my friend Saishri had told. We are first taking the input, we cropped it and then augmented it, but that didn't give us good accuracy. So first what we did was we just augmented the input data and then we cropped it while loading it. And then yeah, then we have the classes, group classes. These are the labels for the group classes. Yeah, we have the input image size of like 966 images, and now we are plotting the training set. So each row in this images is belongs to the one classes. So there are 34 classes using which we are training the data. And now we are loading the inference image. We are doing the same pre-processing as we did for training set. And we are printing the images, plotting them. These are the inference images. Now over to Shreya.
Yeah, this is Shreya. So after the pre-processing and loading the data set, we'll be building the model. So basically, we are using a convolution 2D layer, dropout layer. We use a dropout layer because it chooses a random neurons and it ignores during the training. So basically, we are using a dropout rate of 50%, and this helps in overcoming the problem of overfitting. Then we build the model and we print the summary of the model. So we've included 2,42,000 parameters. And then we compile the model, and we have used the optimizer as Adam and loss as categorical cross entropy, since it's a multi-class problem. Then we've also used the early stopping, which provides as to how many epochs can be run before the model tries to overfit. And we are training the model here where we've used the batch size as 21 and epoch as 40, but that actually depends on the early stopping, as I said earlier. Then we are using the validation split as 20% and the training split as 80%. So, yeah. Yeah, so we can see that we have got the training accuracy of around 92% and validation accuracy around 96%. And now we'll be plotting the accuracies and loss. Uh, yeah, so this is the plot of accuracy and loss. And then we'll be testing the inference data on the model. So we'll be Yeah, we got around 42% accuracy. Yeah, then we predict the cases and we print the top three correct predictions. So basically here the predicted one shows us that it's how much. So predicted one is the first percentage, like it gives us the highest percentage match. Then accordingly uh, it's around 97%. Then yeah, the next part will be explained by Yogya.
This is the end of part A, where we have designed the model, and now coming to the part B. So the current model that we have made runs in the RAM of your systems, and RAM is a volatile memory. If you want to run this network on a different device, then you have to save the program instance to your disk. To do this, you have to freeze the network. Freezing the network is basically converting the current variables and edges into a graph where you have all the weights as constants and which are like nodes, and the edges as a graph. So that is what we did here. We freezed it, and then we convert into .pb. .pb file is basically the serialized structure data in which TensorFlow stores its freezed graph. So we have generated the pb file. Now that we have generated the pb file, the OpenWinnow only accepts the graph in terms of .xml or .bin file. So to convert this to a .xml or .bin file, we need to use Model Optimizer, which is already provided by OpenWinnow, and we have already downloaded it. So now I will run a command where this is a Model Optimizer, and the input is basically our .pb file, and the output directory is where it has to store, and input shape is basically our image is a 32 cross 32 image. Let me go to this first.
_1.
Yeah, 1 minute.
Python.
Oh yeah. Okay, so I saved it as Acute Infarcts instead of Infa. My mistake. So change the name. So yeah, it got the XML and .bin file. Now this is the end of optimization. Now comes to the inference engine. So inference engine is just a library that is present in either C++ or Python. So what we have to do is, our job is now to infer data, that is give an input image and your network has to give you an output of the predicted location. So to do this, we have to write a Python code in which we use inference engine module or a library that they provide. So before running that Python file, we need to activate the environment of OpenWinnow. That's the reason we have to execute the setup var variables, basically batch file. Let me do that. Now to run the inference file, I have to go to its location and running the file. So let me remove that wrong underscore text whatever stuff and run it again. Yeah.
Increase that.
Oh, size. So we have given an input and it predicted it correctly. Right frontal, right temporal, right partial-temporal lobe or something. So it predicted it right. All of them belong to the same class, right?
Okay.
Yeah. So this is the end of our project. Thank you. How to start this?